Okay, here we have two boxes, 15 kilogram box and a 30 kilogram box. I'm going to call the larger one big M and the smaller one little m. And they're sitting on a table or the ground or whatever. We're trying to figure out the normal forces between the boxes and between the lower box and the table. So we'll start with the system schema. So we have that little m box and the big M box, and we have, I'll just call it the Earth. I could separate the table out as a separate object, but there's not really any need to. So there's a normal force between the table and the big box, and there's also a weight, of course. There's gravitational interaction also between the little box and the Earth, but no normal force, because the little box is not actually touching the table/Earth. Guess I should call this Earth/table. Combine that as one object. These two boxes are pushing on each other. I'll call that NB for n between the boxes. So now I'm going to start with free body diagrams. I'll start at the top. So I should have a normal force up and an mg down, and they are balanced because the boxes are in CVPM. They're not moving, or they're not accelerating or moving. Acceleration is the important part. So I know in particular this one's balanced. So when I write my net force equation for little m with up as positive, I'm going to say NB minus mg. And I know it equals 0 because they're balanced, because they're not accelerating. Okay, for the lower box, there are three forces acting. There's this NB, that's the Newton's third law partner of that one. So the big one pushes up on the little one therefore pushes down on the big one with the same size force, opposite direction. There's a normal force up from the table and an mg down. So this is a bigger mg, so I'm going to make it a longer vector than that one was. And then I'm going to make this one long enough to balance those. So my net force equation, also having positive up. NT up minus NB because it's down, minus big mg because it's down, also equals 0 because this one's not accelerating either. Okay, so at this point, if you want, you can put in some numbers of things that you know, and then solve for your normal forces. So this is NB minus M here is 15 kilograms. G is 10 newtons per kilogram. So NB minus 150 newtons equals 0, which tells me pretty quickly that NB is 150 newtons. NT is unknown. NB is now known as 150 newtons. And mg, this is big M, so that's 30 kilograms times 10 newtons per kilogram. So NT minus 150 newtons minus 300 newtons equals 0. And now we can solve pretty easily that force is 150 newtons. So it might be tempting to call this normal force here a weight, but it's really not. In this one particular case, it happens to be equal to that upper weight, but it's not accurate to call this a gravitation. Call this a weight. You can only ever have one weight per diagram because the weight is the interaction between the Earth and an object, and this weight is the interaction between the Earth and that object, not this object. Also, they're just not always equal. They're only equal in some sort of simple circumstances. For example, this normal at the table here is not equal to this weight. And if the boxes were accelerating, even these two would not be equal. So you're just not safe calling ever having two weights. There's always ever only one weight per object.